Hello everyone, welcome to the third lecture in the series. This lecture is to be on the topic complexity of algorithms. So, in this lecture we will be studying how to analyze the performance of algorithms. I hope in the last two lectures you might be thorough with what problem is, how to solve with the help of algorithms. We learnt the operations that could be performed on data structures and what are all the various data structures. So, in this lecture we will be covering up, given a problem, we will have multiple ways of solving the problem which is actually governed by some algorithm, and we are going to analyze and compare the performance of two algorithms with the help of asymptotic notations. This is going to be the organization of this lecture. At first, we will be seeing a quick introduction on analysis of algorithms and its need. Then we will be studying what asymptotic complexity is and what are all the asymptotic notations. So, in this lecture we will be learning only 3 of the asymptotic notations. Then I will be introducing you what are all the complexity classes available, and then we will be seeing in detail how to perform algorithm analysis for different classes of problems. So, in the last lecture itself you know what algorithm is. We learnt the definition for algorithm. Algorithm is actually a step by step way of solving a problem, and you know in the last class we studied how to write an algorithm. So, these are the characteristics of a good algorithm. In general, we say an algorithm is as good only if its running time is less and it should consume a less amount of memory. Of course, I hope that you will remember in the last class I introduced two parameters for measuring the performance of an algorithm. One is time complexity and another one is space complexity. So, time complexity is the amount of computing time or the processing time required by an algorithm to solve a problem, and space complexity is the amount of space your algorithm may demand in main memory. So, of course, these are the two parameters with which we have been measuring an algorithm's performance, and among these two we give more importance to time complexity. It is because it deals with the processing time, that is the time it takes for the CPU to execute the particular algorithm or the program. So, in general we expect an algorithm to be good in terms of both time as well as space, but of course, the most important thing we expect is time. And this slide is about measuring efficiency of an algorithm, and we always measure the efficiency of an algorithm in terms of the amount of computing resource it consumes. So, given a problem, the problem may take an input of size n, and we measure the complexity of an algorithm based on its problem size. So, always complexity of an algorithm is a function of problem size. And as I mentioned before, the most important thing we are interested is on time than space. So, we will be analyzing or measuring the efficiency of an algorithm in terms of how much processing time your algorithm would demand. And there are certain other factors which also have some impact, or they also play a vital role in terms of efficiency of an algorithm. For instance, the hardware on which you actually run your program, the underlying operating system, the compiler with which you actually compile your source code into its equivalent object code, the size of the input, the nature of the input, and finally the algorithm. And so, now we are looking at only the algorithm and the size of the input to analyze the efficiency of an algorithm. This slide we see the running time of an algorithm. So, what are all the factors that actually have much impact on the running time of an algorithm? As I said before, we are going to restrict our attention to the input size and the nature of the input. So, as you know, generally the running time of an algorithm increases with the size of the input. For instance, imagine that you have some 5 elements to sort, then that may take you some microsecond, and if suppose you may have to sort some 5 lakh elements, then in that case the time that would that the processing time required for doing that task could be more than what it takes for 5 number of elements. So, that is why we say that the time always grows with the size of input. In order to measure the running time of an algorithm, we usually go with two ways. One is, we may either take the number of steps that is part of an algorithm. We may compute the number of steps that is part of an algorithm, or we may be interested in looking at the primitive operations performed by an algorithm. So, we will be doing two things, either the number of steps in an algorithm or the number of primitive operations involved or performed by an algorithm. And of course, we ignore certain other factors like the machine on which you actually run your algorithm and the underlying operating system. So, in order to measure the running time of an algorithm, we are going to see the input size and the number of steps your algorithm is actually involving, and as well as the number of primitive operations that are part of that algorithm. In this slide, I have given you a simple algorithm. I have given you an example of how to do an algorithm analysis. So, as we know before, the running time is a measure of number of steps or number of primitive operations performed. By primitive operations, we mean it could be any of the elementary operations like addition, subtraction, multiplication, comparison or assignment. All these fall under basic or elementary operations. So, we will be measuring the number of steps or the number of primitive operations given an algorithm. So, in the middle of the slide here you could see I have given an example. So, in that example we are actually computing the sum of an array of n elements. So, we have a function named sum. It takes as input an array named A and its size is going to be n. And initially we initialize the variable s to be 0, and then we have a loop that iterates n number of times. So, in that loop we actually compute the sum of every element and accumulate it with the variable s, and finally we return the value of sum that is captured in the variable s. Now, we have to analyze this algorithm. So, as you see on the right side under 3, I have given something in green and something in red. So, let us see whatever I have given in red. So, whatever I have given in red is the actual amount of primitive operations involved in that algorithm sum. So, you could see that there is the first statement int s is equal to 0, which is an assignment. So, assignment is one of the primitive operations. So, I have named it as 1. Similarly, in the for loop statement you have 3 primitive operations, 1 an assignment, now the 3 is actually a comparison, 4 is actually an increment operation. And within the loop you have a statement s is equal to s plus a of 5, and in that one statement we have 3 primitive operations involved, which are labeled as 5, 6 and 7. And finally, we have a return statement which has one primitive operation, return operation, and so we have numbered it as 8. And as such, the entire algorithm has 8 primitive operations involved, and of course, you could notice that the first statement int s is equal to 0 is outside of the loop, and that statement will get executed only once. And we have a for loop which involves 3 primitive operations, and you know the initial assignment, that is I equal to 0, as well as the final statement, that is return, those two will get executed only once. And so, we have named it as 1, 2 and 8, all these primitive operations will be executed only once. Other than that, the primitive operations from 3 to 7 will get executed once during every iteration. And you know this loop iterates for n number of times, and so these 5 primitive operations will have to execute n number of times. So, finally, we sum up the number of times each of these primitive operations get executed, and so we know that 3 to 7 gets executed for n number of times. So, 5 operations n number of times, which is 5n, and the first 3, that is 1, 2 and 8, get executed exactly once, and so it is 5n plus 3. So, if we are measuring or representing the complexity of an algorithm as a function of primitive operations involved, then f of n is the complexity function. We say the complexity function as f of n, where n denotes the size of the input and the complexity function is 5n plus 3. Similarly, we can also measure the complexity of an algorithm as a measure of number of steps. So, let us do the same, let us consider the same example and compute the number of steps that is part of this algorithm. So, by number of steps we mean how each of those statements, how many times each of those statements get executed, and so you know within this function we have 4 statements. The first line, that is the first statement, gets executed exactly once, that is why I have shown with green. The for loop, it gets executed n number of times, and whatever condition, whatever statement that is within the for loop, that will get executed n minus 1 times. So, why we say the for loop is getting executed n number of times is that n minus 1 times the loop condition would be true, and the last time the loop condition would be false. So, it is n minus 1 plus 1, which is n, and whatever statements that are present within the loop will get executed exactly n minus 1 times, and so we say that the statement within the loop has n minus 1 steps, and the last statement being a return, it will get executed only once. So, when we sum up, we get f of n as 2n plus 1. So, this is how we measure the complexity of an algorithm as a parameter of the number of steps involved. So, we learned 2 ways of analyzing an algorithm, one by measuring the number of primitive operations and the other by measuring the number of steps involved in that algorithm. And as you know, if the size of the input keeps on growing, then the number of steps that algorithm would take will be a linear proportion to the size, that is the input size n. So, we say that this function is of the order of n, the complexity of this algorithm, this particular algorithm sum is an order of n. Now, I introduce before you what asymptotic complexity is. Asymptotic complexity is actually a mathematical method to measure how and efficiently an algorithm scales with increasing input size. So, in maths we have several algorithm classes, we have several complexity classes, and we are going to make use of that computational classes for in order to express the efficiency of an algorithm. So, in the previous example we saw or we measured the algorithms, I mean the complexity of this particular algorithm sum to be f of n is equal to 5n plus 3 when we took primitive operations, and we measured f of n to be 2n plus 1 considering the number of steps. So, asymptotic complexity we were using n, I mean in the last example we used we computed the asymptotic complexity for the function named sum, and we measured f of n to be 5n plus 3 given by considering the amount of primitive operations, and we measured the complexity to be f of n is equal to 2n plus 1 by considering the number of steps involved in that algorithm. But when we are going to express the same using asymptotic complexity, we will be concentrating only on the higher order terms. So, in that f of n is equal to 2n plus 1, we will be ignoring the constant part, and we will be also ignoring the coefficient that is part of the highest order term. So, we say that the algorithm's complexity is of the order of n, and we are using this asymptotic complexity to get an approximation on the complexity of that algorithm. And of course, we actually mentioned that we will be ignoring many of the other factors that also have an impact on an algorithm's performance. We will be ignoring the machine details and we will be focusing only on the bigger picture, which is the size of the input and the nature of the input. And we are going to study 3 asymptotic notations in this lecture. The first asymptotic notation is big O notation, and as I said before, asymptotic notation is a mathematical way of expressing complexity and it is actually an approximation, and this big O notation is actually used to express the upper bound of a function. So, we are going to say the worst case complexity of an algorithm with the help of this big O notation. Now, we will see what this definition of big O notation is. If suppose we have 2 complexity functions f of n and g of n, we say that f of n is equal to big O of g of n if there are constants c and n naught such that n is greater than n naught. Then we say that f of n is less than or equal to c into g of n for all sufficiently large n. So, here what we say is that we are having 2 functions, complexity classes f of n and g of n, and we are defining the upper bound for this function f of n. We have computed the complexity class for a particular algorithm or a function which is f of n, and we say that its upper bound will always be less than or equal to c into g of n. So, given an algorithm's complexity as f of n, when we say its worst case complexity, we will just specify an upper bound and we will say that the algorithm's performance will never exceed the c into g of n on any account irrespective of the size of the input. So, that is what we denote with big O notation, the upper bound of a function. In this slide, we have a way for comparing 2 functions. So, here what you see is a graph. In that graph, we have compared the performance of 2 algorithms, and this graph makes a comparison of input size and the time, that is the number of steps involved as a part of that algorithm. At one particular instance, say n equal to 60, which is the size of the input is 60, we have seen that there is one algorithm which has resulted in a complexity of f of n is equal to 3n, and there is another algorithm which has resulted in a complexity of f of n being 0.05 n square. So, we say that this algorithm's complexity is order of n and the other algorithm's complexity is order of n square by just ignoring its coefficients. So, if someone asks you to make a comparison of which of these 2 algorithms is good, then you would blindly say that the algorithm whose complexity is order of n is the best. So, here we will be studying about complexity classes in later part of this presentation, but what we mean here is that even though the algorithm, say in this example, an algorithm has a complexity of 7n minus 3, in that case it is always right to say that this algorithm's complexity is always less than n cube, because we know that order of n is always less than order of n cube, but always there is a necessity to make approximation as tight as possible. So, it is right for us to say that 7n minus 3 is closest to the complexity class order of n than order of n cube, and in order to keep this approximation as tight as possible, we will say that 7n minus 3 is approximately equivalent to order of n. So, here we have a problem. We are asked to prove that the running time of an algorithm is T of n is equal to n cube plus 20n plus 1. This is equivalent to order of n cube. We are asked to prove that the function is order of n cube. So, we are going to apply the definition of prove this with the definition of big O notation which we learned before. I said that the function f of n is always less than or equal to c into g of n. So, in this case our f of n is n cube plus 20n plus 1 and our g of n is n cube. So, that is why we have put up in both sides of this relation t of n is less than or equal to c into n cube. And then in order to prove that further, what we do is we apply, we divide the entire thing on the left hand side by n cube in order to get this. And in that big O notation we have a assumption that n is greater than n naught, which is equivalent to 1, and we have set up a value c which is greater than or equal to be 22. So, in our case whatever be the value we apply for n, on any account it will be always less than 22 in our case, because that is the value we have set up for c to be either 22 or any value greater than 22. So, whatever be the value you give for n, on any account it will be lesser than the value you fix up for c, and that is why we say that this algorithm's complexity is of the order of n cube. But merely given, after estimating the complexity of an algorithm either using the number of primitive operations involved or using the number of steps involved, we will be able to derive a function, and whatever is the highest coefficient in that complexity function is going to be the order of the complexity order of the function. And what you see on the underlying graph is the different complexity classes available. As I said before, this is actually drawn from mathematics, and that is why we measure algorithm analysis, we perform algorithm analysis in terms of asymptotic complexity. So, this is what the various classes of complexities. We have complexity of the order of 1, which we call it as a constant algorithm, and we have complexity class order of log n, which we call it as logarithmic, complexity class of order n, which we call it as linear, complexity class of order n into log n, which we call it as log linear. We have complexity class of order of n square, which is quadratic, complexity class of order 2 power n, which falls under exponential, and the worst case could be order of n factorial. And of course, you could see that in all those cases we measure it in terms of input size n, and then we may be fitting it to any of these complexity classes, probably by finding the closest the complexity class which is in close proximity to the computational complexity which we have found. The second asymptotic complexity notation is big omega notation. As we learned before, we learned about big O notation, and I was telling you that it is used to find the upper bound of a function. Similarly, we have another notation, big omega notation, which is used to express the lower bound of a function. So, always big omega notation is used to express the best case of a algorithm. Whatever be the input size, the minimal time it takes could be the best case of a particular algorithm, and big omega notation is used to express such lower bound of a function. Now, let us see the standard definition available for big omega notation. So, we have two complexity functions f of n and g of n. In order to express the lower bound for this function, we say that if f of n and g of n are two complexity functions, then we say that f of n is omega of g of n if there exists some positive number c and n naught such that f of n is always greater than or equal to c into omega of n. So, the difference lies here on the sign. Earlier it was less than or equal to, now we say it is greater than or equal to, just because we are expressing the lower bound of a function, and this has to be true for all values of n greater than n naught. So, here you could see from the graph, we are going to find the lower bound for this function f of n, which is going to be omega of g of n. So, here you could see we have an example, f of n is 32 n square plus 17 n plus 1, and in this case if I am asked to find the lower bound for this function, here it could be both n square or n. If suppose we choose the value of c as 32 and n naught as 1. It could be something like omega of n square or omega of n, both can be its lower bound, but it can never be omega of n cube. This is because in the previous case I was telling you the various complexity classes available. We have n, n log n, n square and then n cube, then 2 power n, right. So, when we talk about lower bound, it should be something lesser than that available at the higher bound. So, anything for instance, if suppose my upper bound is big O of n, then my lower bound could be either n or log n or 1, but achieving 1 is always not feasible. We say an algorithm to be having a constant time only if its running time does not vary with the input size. Such a scenario is not possible. So, if suppose a function's upper bound is big O of n, then its lower bound could be either big O, I mean omega of n, or it could be something less than that, which is log n. Next, we introduce the third asymptotic complexity notation, which is big theta notation. If suppose we are asked to express a tight bounds, that is the boundary, the higher and the lower bounds, then it is good to represent the same using a big theta notation. So, the theta notation's definition goes this way. We say we are given with two complexity functions f of n and g of n. We say that theta of g of n is equivalent to f of n when there exists positive constants C1 and C2, such that C1 into Gn is always less than or equal to f of n, and which is less than or equal to C2 into g of n. So, given a function f of n, we are just defining its upper bound and the lower bound with the help of this theta notation. So, this slide shows a quick comparison of the different asymptotic notations which we learnt earlier. Big O notation is used whenever we are interested in knowing the upper bound of an algorithm. Omega notation is used whenever we want to express the lower bound or the best case complexity of an algorithm, and theta notation is used whenever we want to have a tighter bound, that is upper and lower bound. So, we will be specifying a function's complexity will not go below this or go above that. So, that is what we represent with the help of theta notation. And here is the summary which we could make for asymptotic notations. A function f of n is equivalent to theta of g of n when both f of n and g of n grow at the same time or same rate asymptotically. If we are given with two functions and if they both grow at the same rate, then we say that f of n is equivalent to theta of g of n. We say f of n is equivalent to big O of g of n only if f of n is asymptotically slower growing than g of n, that is we are defining the upper bound for that function f of n, and we will be using f of n is equivalent to omega of g of n. Then we say that f of n is asymptotically faster growing than g of n, that is we are saying its lower bound. Now, we may have a question, which among these notations should we have to use when we think of analyzing our own algorithm? As a computer scientist, we will be normally expressing our algorithm's performance in terms of big O notation, that is we will be specifying the upper bounds of our algorithm. The reason is that as I said before, big O notation actually gives a picture of the worst case complexity of an algorithm. We are much interested in knowing the worst case just because only then we will be having or looking at some ways for improving our algorithm and try to make our algorithm the best. So, whenever we make or develop an algorithm, we normally measure the number of primitive steps that are part of an algorithm and express the same using big O notation. And these are the different complexity classes available. As I said before, the first complexity class is f of n is equivalent to 1 or any value which is a constant. So, in that case it means that the running time of such an algorithm is going to be fixed and it is not going to vary with the size of the input. But writing an algorithm that takes a constant time is always not feasible. The second complexity class is log n, which is logarithmic class. Here when n increases, that is the size of input increases, the running time will also increase, but the increase is much slower. And I hope you might have learnt about binary search. It is in that case, in case of binary search, we initially keep the elements sorted, and then we, depending upon the element to be searched, we make our search space to be either left half elements or right half elements. On any account, we will not be making a search on the entire list of n elements, rather we will be making our search to any one half of the list of elements, and so it falls under the category of an algorithm whose running time complexity is log n. The third complexity class is n, which means linear. So, in this case we say that the runtime varies in proportion to the size of the input n. If suppose n size is small, then the processing time will be less, or else it would be more. The linear search algorithm is a best example for an algorithm with running time to be linear. And then we have the next computational complexity class, which is n into log n. So, in this case it would be slightly more than what we had for linear. It is going to be n into log n, and which will be roughly closer to even double the size of input. So, the best example for this complexity class is merge sort. The next complexity class is n square, which we call it as quadratic. So, here when the size of input gets doubled, the runtime will get increased 4 times. And we have another computational complexity class as n cube, which we call it as cubic, and most of the operations which we do on a matrix fall under this computational complexity class. Then we have complexity classes 2 power n, which is exponential, and so here runtime will get doubled or multiplied even more, and this whatever algorithms that do brute force will fall under this category of exponential. Having learnt the various complexity classes, now we are going to study how to do algorithm analysis. So, in our algorithm or in our program or a function, whatever we write, mostly we will be coming across some statements or loops. There will be some portion of code where we will be doing some we will be having some statements doing some computation, or we may have some loops in our code, right? And we are going to study how to do algorithm analysis in each of these cases. The first thing is the statements which usually take a constant amount of time. There can be statements in your code which are highly independent of the size of input, and those statements will always take a constant amount of time in your algorithm. For instance, you may have some statements which fall under the category of assignment statements. Some may be doing arithmetic operations, some may involve array referencing, some may do some assignment to an array element, and we may even have some statements for doing some conditional testing. So, all these statements usually take a constant amount of time, and we call them as constant time statements. Next is we may encounter loops in our code. So, here I have given an example. You could see a for loop that iterates for 100 number of times. So, here 100 is a constant. So, it does not depend on the size of the input. So, we may have some loops that get executed some constant amount of time. So, here the loop executes for 100 times, and so I say that it is order of 100, which is actually a constant. So, we say that it falls under the complexity class of order of 1. So, here we have another loop, we have a while loop that runs for n number of times. So, here we have to measure the complexity in terms of step size. So, here we have one statement above the while loop which executes one time. So, it is 1, that is what I have, f of n is equal to 1 plus, and we have the while statement that iterates for n number of times, and iterates for n number of times. So, it is n minus 1, and then we have some statements within the while loop that gets executed n minus 1 times. So, here we have marked some statements as list of sequence statements which have actually c number of steps, and that is why we have c into n minus 1, plus there is an increment operation which actually takes n minus 1 time, which actually runs n minus 1 times. So, when I sum up, I will have the algorithm's complexity as c plus 2 into n minus c plus 2 plus 1. So, in general, when I look at the highest order term, it is going to be n. So, we say that the algorithm's complexity is order of n. Next, we have to see what we have to do in case of conditional statements. Whenever we have conditional statements in our code, depending upon how the condition gets evaluated, we may either execute statements either that are part of if, or if the condition fails, we will be executing statements that are part of else. So, if suppose we have statement 1 that runs for order of n time and statement 2 which executes for order of n square time, in that case, since only in runtime we will be knowing which of these two will get executed, and for the safer side, as we are estimating the upper bound of an algorithm, we will always take the highest one, which is order of n square. Next is with respect to recursive functions. At times we may even have recursive functions in our code. So, whenever we are having recursive functions, then we may have to use recurrence relations to compute its complexity function. So, here we have a function named power that is used to compute the power of some number. So, here if suppose we have the value of n, that is the input size to be 1, then exactly this algorithm will have a running time of t of n, which is 2. If suppose n is greater than or equal to 2, then this recursive function may have to call again and again till n becomes 0, right. So, in that case, if n is greater than 0, then this function t of n is going to be the running time when t of n is equal to 1 plus for all other cases. So, we say that t of n is equal to 2 corresponds to n equal to 1, and remaining is t of n minus 1 for all n greater than or equal to 2. So, this is going to be the complexity for this recursive function. So, here how this could be proved with the help of back substitution. As I said before, when n is equivalent to 1, our t of 1 is equivalent to 2. Now, we have to find what if t of n is greater than or equal to 2. In such cases, we may have to expand this t of n is equivalent to 2 plus t of n minus 1. Now, we apply the same value, that is we apply the value of t of 1 to t of n minus 1, and so we will be expanding this again to be t of n minus 1 is nothing but 2 plus t of n minus 2, and if I try to expand t of n minus 2, that is going to be 2 plus t of n minus 3, and this keeps on going, right. So, when we try to expand it, we will be able to see some pattern, and from that we will be able to conclude that t of n is just 2n plus 2, and so we say that it is order of n. So, here what we understand is that whenever we have some recursive function in our code, then we may have to use recurrence relations to compute the algorithm's complexity. So, here I have given you two questions to understand to test your understanding on algorithm analysis. You could see here we have two for loops. The first for loop iterates for n number of times, and the second for loop also iterates n number of times. So, if you are asked to measure the algorithm's complexity, let us consider that we use number of steps involved. Then in that case, the first statement will get executed one time, the second statement for loop will get executed n times, and the third statement, which is a for loop, which will get executed n times, and the last statement sum plus is equal to k plus j will get executed n square times. So, when we sum up all these, then it would be 1 plus n plus n plus n square. So, which is n square plus 2n plus 1 So, of course, we are interested in the highest order term, and so the complexity of this piece of code is order of n square. The second question is, what is the complexity for finding the sum of first n numbers? So, you could imagine this implementation of this task to be having a for loop with just one sum statement within, and so here the loop may have to run n number of times just because we find the sum of first n numbers, and so we say that this particular function would take order of n. So, that is how we measure algorithms complexity. So, to summarize, we learnt about algorithm and how to measure its complexity. Though we have many factors, we restrict our attention to the size of the input and the nature of the input. And I told you that asymptotic complexity is a mathematical way of describing a behavior of an algorithm in terms of its running time, and we measure how the algorithm behaves when the input size keeps on growing, and we denote the input size as n. And whenever we represent an algorithm's complexity, we will be eliminating all the constants, and we will be eliminating the coefficients of the higher order terms, and we will be restricting our attention only to the highest order term and map that to any of the available complexity classes. And we learnt about three algorithmic asymptotic complexity notations. One is big O notation, and I told you that it is used to represent the upper bound of an algorithm, or in other words I would say that we represent the worst case of an algorithm with the help of big O notation. We learnt about omega notation, big omega notation, which is used to denote the lower bound of an algorithm, or in other words we would say that we represent the best case of an algorithm with the help of big omega notation, and theta notation is used to express a tighter bound. And we will be learning about the next topic, arrays, in the next lecture. Thank you.